I would like present a numerical analysis. In this investigation, I use the nonlinear finite element method is called Abaga's software. And in this software, seismic load, which is selected from the literature and is collected in earthquake station, is used and applied to the model. And one tip of the soil is unsaturated soil is used to simulate embankment and subsoil. In subsoil, we have two models. The first one is unreinforced and second model is reinforced. In reinforced soil, geogrid sheet is simulated and geogrid is installed on the toe of embankment. The distance between any sheet grid is 5 meters. Total five sheet grid is used, and height of the subsoil is 30 meters. And sheet grid has only one direction element, and each element has 2 meter distance. And crack also is developed only in subsoil exactly below toe of embankment. And when seismic load is applying to the model, both for reinforced and unreinforced subsoil, the crack is there. And geogrid is a function on expansion, controlling expansion of the crack. And here, the first and top picture, embankment subsoil is modeled and it's shown with the scale. The length of the subsoil is 160 meters with height of 30 meters. And in second part, we have a embankment subsoil with the crack. And X, Y, and Z direction is showing in this picture, and the seismic load is applying to the model in X, Y, Z direction simultaneously. What kind of seismic load is applying to the model? Seismic load is showing in this picture. An earthquake of 6.2 magnitude we have here, and data is collected from the earthquake station. And from 2 to 6 seconds is a critical part of this seismic loading. This part is applying to the model in numerical simulation analysis, nonlinear numerical simulation. And at this next picture is showing the mesh from the top view of embankment and subsoil. And this kind of the mesh is using for simulation of the impact of the seismic load on the model. In the brief, we have left side of this slide a brief flow chart for this investigation. At the first, collecting seismic data from earthquake station, and second one is the modeling. We have two models here, reinforced and unreinforced subsoil, and calculation of displacement and strain using our software, assessment of the result. What is the result? What we find here, And after assessment, the prediction of future response of the embankment subsoil for the design of this structure. Let's move to the result we have here from the finite element method. In the first, at the top, we have maximum displacement 193 is a displacement in vertical direction, and the second part is second picture displacement is 183. 10 is a reducing the displacement when the subsoil is reinforced subsoil. It's one. And second thing I got here from this numerical simulation, the crack expansion. The crack expansion in unreinforced subsoil, the crack expansion is bigger than compared to the crack expansion in reinforced subsoil. Reinforced subsoil and using reinforcing subsoil and using geogrid is controlling of the crack. In this investigation, only geogrid sheet is placed on the toe of embankment. Is need to find exactly which place has higher crack and in which location we need to put geogrid. It can be future research work for this investigation. And in a strain, we have a same result. When we have a strain, we have two different mechanisms of strain. And in reinforced subsoil, same displacement, strain same displacement is reducing, and crack also is, we have less crack when we have geogrid in. Okay, the next part is the displacement and strain in whole stage of the numerical simulation. In whole stage of numerical simulation, we have the displacement at the first, the mechanism of displacement in whole stage of numerical simulation for model 1 and model 2. Model 1 is unreinforced subsoil and model 2 is reinforced subsoil. Is a different. When the mechanism of displacement is different, it means mechanism of vibration and deformation are different. The nonlinear deformation is changed when the model is reinforced using the geogrid, and same we have here in the strain. Okay, novelty of the present work related to the methodology for identification in which location of subsoil it need to have geogrid sheet for minimizing construction cost and minimizing of the embankment and subsoil collapse. The seismic, it will be seismic resistance of embankment and subsoil is increasing if we use right place of the reinforcing subsoil. In the future research work, what we can do in the future research work can be done based on the using different type of the soil. We use one type of soil, different type of soil, or simulating of embankment and subsoil based on the real embankment and subsoil. We can collect data from the field or literature and applying different seismic load to the model, designing of geogrid geometry. In this investigation, the size of the display, the size of the geogrid sheet was 5 meter, and each geogrid element has 2 meter distance, and geogrid has only in one direction. It can be different direction, different geometry. And when this geogrid sheet distance is less and the geogrid sheet element used with a small distance, there of course the displacement is reducing and we will have the less displacement, but it should be economic design of the geostructure is a very important. And in the next part of the designing of the geogrid and geogrid sheet in embankment, we need to understand exactly location we need to install geogrid. Thank you for attention. If you have any question, please email me.